Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. My name is Azmat Ali and I welcome you all in class of Elementary Number Theory by David M. Burton. In today's lecture, we will discuss three important examples from the book of David M. Burton. These are very interesting examples. The first example is we have to show that the square of an integer is always either of the form 4k or 4k plus 1. Alternative way to express the above statement is that if we divide the square of an integer by 4, it leaves the remainder 0 or 1. You can take any integer and when you divide its square, it always leaves the remainder 0 or 1. For example, if your integer is 4, then its square is 16. If you divide 16 by 4, it leaves the remainder 0. For example, if your a is 3, your square is 9. If you divide 9 by 4, your remainder is 1. So when you divide the square of any integer by 4, it always leaves the remainder 0 or 1. So if the remainder is 0, it means your integer is exactly multiple of 4 and you can assume this is equal to 4k. Your integer is 4k. And if it leaves the remainder 1, it means your integer is of the form 4k plus 1. So let a be an integer, then there are two possibilities for a. It is either even or odd. In case when a is even, we assume a is equal to 2k. Now its square is 4q square, where as q is an integer, so its square will also an integer. So we suppose q square is equal to k. This is equal to 4k. When a is odd, in this case, we suppose our a is of the form 2q plus 1, where q is an integer. Its square is 2q plus 1 whole square, which can be written as 4q square plus 1 plus 4q. By taking common 4 from these two expressions, we have 4 into q square plus q plus 1. As q is an integer, so its square is also an integer and sum of two integer is again an integer. So we suppose q square plus q is equal to k. So this can be written as 4q plus 1, which is required. Next, we show that the square of any odd integer is of the form 8q plus 1. Now, in this case, we have to calculate the square of odd integer. While in the first example, we have calculated the square of any integer. So, this is the these lines before the proof shows the story. When we divide an integer a by 4, then the possible remainders are 0, 1, 2, 3. When r is 0, this shows a is a multiple of 4. That is, we can take a is equal to 4q. When r is 1, then this shows a is divisible by 4 and it leaves the remainder 1 and it can be written as a is equal to 4q plus 1. Similarly, for r is equal to 2, your a is of the form 4q plus 2 and r is equal to 3, your a is 4q plus 3. So here a is equal to 4q and 4q plus 2. Both are the even integers, while a is equal to 4q plus 1 and a is equal to 4q plus 3 are odd integers. So we show that in case when a is 4q plus 1 and a is 4q plus 3, your square is of the form 8q plus 1. So your proof start from here. You can start your proof from here. You can write, suppose a is of the form a is equal to 4q plus 1 and a is equal to 4q plus 3. Then we show that its square is 8k plus 1. Consider the first case when a is 4q plus 1. By taking its square, we have 16q square plus 8q plus 1. Taking 8 common from first two terms, we have 2q square plus q plus 1. As q is an integer, so this sum is also an integer, and we say this is equal to k. Hence, this is of the form 8k plus 1. In case when your a is 4q plus 3, again by taking square, we have 16q square plus 9 plus 24q. By taking we can break 9 as 8 plus 1. So taking common 8 from these three terms, we have 8 into 2q square plus 3q plus 1 plus 1. As the sum of three integer is again an integer, we suppose this is equal to k. Hence a square is again of the form 8k plus 1. So in any case, when your a is an odd integer, its square is always of the form 8k plus 1. You can verify it by any simple example. Suppose my odd integer is 7. If you divide 7 square, that is 49 by 8, this is equal to 8 6 is 48. Your remainder is 1. So by doing an algorithm, you can write 49 is equal to 8 into 6 plus 1. Here 6 is represent k and 1. So this is the form of 8k plus 1. Similarly, when you divide 13 square, which is 169 by 8, it can be written as in this form 18 to 21 plus 1. In the next example, this is also an important example. Show that the expression a into a square plus 3 over 3 is always an integer for a greater than or equal to 1. You can prove it by mathematical induction, but we will prove it here. By doing an algorithm. As the denominator of this fraction is 3, so we can I am writing here, according to division algorithm, every integer a, when it is divisible by 3, it is of the form 3q, 3q plus 1, 3q plus 2. Uh, in, it will be 3q when a is exactly divisible by 3. If it leaves a remainder 1, then a will be 3q plus 1 form, and when it leaves a remainder 2, then a has the form 3q plus 2. So we assume all cases here and show that in every case this number a into a square plus 2 over 3 is an integer. When your a is 3q, so plug in this value of a in here, this becomes 3q, 3q whole square, that is 9q square plus 2. By cancelling out 3 here, this gives q into 9q square plus 2. As q is an integer, so this sum of product, uh, this product, sorry, is also an integer. When your a is 3q plus 1, so plug in this value of a here, this gives 3q plus 1, and when we put here 3q plus 1 and expanding its square, 9q square plus 1 plus 6q plus 2. 1 plus 2, this is 3. By taking common 3 from these three terms we have, and by cancelling out this, I have this product. Clearly an integer by using the fact that product of two integer is an again integer. As q is an integer, so sum of 3q plus 1 is also an integer, and similarly these three terms are also an integers, and the product of two integer is again an integer. Lastly, in case when your a is 3q plus 2 and plugging this value of a is equal to 3q plus 2, you can arrive at this step, which is clearly an integer. Hence, for all a greater than or equal to 1, this number is always an integer, and it completes the proof. So, I hope now you have a clear understanding of these three examples. In the next lecture, we will discuss, we will start problem 2.2. So, if you find my lectures are helpful for you, kindly like, share, and subscribe my channel. Inshallah, see you in the next lecture. Take care. Allah Hafiz.